Have you ever, stood at the mouth of a huge cave or maybe stared down a deep, dark well and just felt that pull?
That ancient fascination.
Exactly, that curiosity about what lies right beneath our feet. For centuries, we've filled that void with some incredible ideas, lost empires, inner oceans, even golden libraries.
And today we're going on that journey. We're going to explore those famous subterranean myths, but then we're going to confront them with the, frankly, shocking reality that modern science has uncovered.
So that's our mission for this deep dive.
That's it. We're holding up the really fanciful ideas, like hollow planets and mythical treasure, right next to the hard data from modern metagenomics and the Deep Carbon Observatory.
And the goal here is to unpack all of it, right?
Right.
We want to give you the surprising facts about the sheer scale of life underground and maybe critique some of those famous myths along the way.
It's a journey that completely redefines what habitable even means.
Okay, so let's start with a concept that sounds like pure science fiction now, but was once, defended by some very serious scientific minds. The hollow Earth.
It's such a compelling idea. And you have to remember, it filled these huge gaps in knowledge we have back before the 18th century.
And the most famous defender of this was?
The renowned astronomer Edmund Halley.
Wait, the Halley's Comet guy.
The very same. In 1692, Halley proposed that the Earth was actually a hollow shell, maybe 800 kilometers thick,
And inside.
more concentric spheres, kind of nested like Russian dolls.
And he wasn't just doing this for fun. He had a scientific reason for it.
Precisely. He was trying to explain these perplexing magnetic compass readings they were getting. He thought shifting internal layers could be responsible.
Okay, that makes some sense.
He even speculated that gases escaping from these inner worlds were the cause of the aurora borealis. It was this elegant, if wrong, attempt to solve the big geophysical mysteries of his day.
So how did science actually prove him wrong? I mean, how do you go about weighing an entire planet to show it isn't hollow?
It started with density. To know the density, you first have to figure out the Earth's mass.
Which seems impossible.
Well, it was tackled by these incredible, painstaking experiments. First by Pierre Bouguer in the 1740s, and then famously by Henry Cavendish in 1798. They basically weighed the planet by measuring the gravitational pull of a known mass.
Like a mountain. Or in Cavendish's case, those lead spheres.
Exactly. Classic physics. And they established Earth's average density is about 5.5 grams per cubic centimeter.
Which is much denser than the rock on the surface.
About twice as dense. So if the Earth were hollow, the overall number would be way lower. The only way to get that mass is if the core is made of something incredibly dense.
Nickel iron.
Right.
Yeah.
And the final nail in the coffin was the seismic data, when we could finally listen to the planet.
Earthquake waves.
Those waves travel differently through liquids versus solids, and they change speed based on density. By timing them, we can map the interior perfectly.
And what we see is a solid crust, a mantle, a liquid outer core, and a solid inner core.
No room at all for Halley's luminous atmosphere or any hidden worlds.
But, the idea is just too good to let go of. And that's where fiction comes in. The ultimate version has to be Jules Verne's 1864 masterpiece, Journey to the Center of the Earth.
Verne was a master at this. He could blend the science of his time with pure, fantastical adventure. The whole story kicks off with a coded runic cipher.
Left by a 16th century alchemist, Aron Saknussemm.
And it promises a route to the Earth's core, to the crater of Snæfellsjökull in Iceland.
And once they get down there, geological reality just goes out the window. Verne creates this absolutely breathtaking prehistoric world.
There's a giant underground ocean.
Where they see these huge marine reptiles battling each other.
A plesiosaur fighting an oversized ichthyosaur. It's just magnificent chaos.
But the peak of it all has to be the giant.
Oh, the 12-foot-tall humanoid figure, just, shepherding a herd of mastodons.
It's glorious, but we know it's fiction. Which brings us to a more modern, more persistent myth. The Golden Library of Cueva de los Tallos.
This is a real place in Ecuador. Cueva de los Tallos means cave of the oilbirds. It's a huge, deep system, known to the native Shuar people for generations.
But the whole treasure myth really takes off in the 1960s with an explorer named Janos Moritz.
Right. Moritz claimed he found this incredible, totally artificial golden library deep in the cave.
And what was in this library?
He described gold books covered in hieroglyphs that he said proved a link to the lost continent of Lemuria. And, even stranger, he claimed it all proved that the Magyar people, his own ancestry, were the origin of all human civilization.
Wow, okay.
Yeah.
That escalated very quickly.
It did. And the story got supercharged when Eric von Däniken featured it in A Gold of the Gods, claimed the tunnels were built by aliens. Moritz himself even claimed that 4 telepathic aliens had congratulated him personally.
So it's this wild mix of pseudoscience and, I guess, wish fulfillment. But people took it seriously enough to launch a massive expedition.
They absolutely did. In 1976, the Ecuadorian and British governments mounted one of the largest cave expeditions ever. We're talking over 100 people, military, scientists.
And the most unbelievable part, Neil Armstrong was there.
Wait, Neil Armstrong, the first man on the moon, went looking for a golden alien library.
He was part of the exploration team, yes. They explored the caves, found some polished passageways, some burial sites from 1500 BCE.
But no golden library?
The archaeological consensus is that it just didn't exist. Morich's claims were, well, a hoax.
So we've got Halley's elegant but disproven science, Verne's fantastic fiction, and a flat-out hoax.
And now we pivot. We move from fiction to the science because the real subterranean world, as revealed by the Deep Carbon Observatory, the DCO, is so much stranger and more massive than any golden book.
This is where we leave human imagination behind. And the reality is just stunning. The core discovery of the DCO is the sheer scale of what they call the deep biosphere.
That's the hidden layer of life, miles under our feet.
And when we say massive, you have to understand what that means. The DCO estimates that this environment holds somewhere between 16.5 and 25 billion tons of microorganisms.
Okay, put that number in perspective for us, for you, the listener.
It's hundreds of times the biomass of all human beings on the planet combined. We are a tiny fraction of the weight of the life that exists beneath us.
So the vast majority of life on Earth isn't on the surface at all. It's not looking at the sun.
Not even close. An estimated 70% of all of Earth's bacteria and archaea live down there. And it's not a thin layer either. The volume of this ecosystem is nearly twice the size of all the oceans combined.
That is an unbelievable amount of real estate. And it's extreme real estate, right? What are the conditions like down there?
There are conditions that challenge everything we thought was habitable. We're talking about microbes, extremophiles, found up to 3 miles deep.
Over 4.8 kilometers.
In crushing pressure, with zero light, and at temperatures that are just astonishing. Some have been found thriving at 251 degrees Fahrenheit.
That's well above the boiling point of water.
Right. The immense pressure keeps the water liquid, but the heat is intense. And crucially, this is life in the ultimate low-energy, low-carbon environment. They have almost no resources from the surface.
Which means they have to be incredibly efficient.
So efficient that they make life on the surface look ridiculously high maintenance.
Which brings up the big question. If resources are so scarce, what are they eating? Up here, it all comes back to photosynthesis. What's the menu 3 miles down?
That's where the metagenomic data gives us the real insight. Scientists analyze DNA from groundwater all over the world, Africa, Asia, Europe, North America, and they found something amazing.
It's not random.
Not at all. It's dominated by a consistent, globally conserved core microbial community, a kind of subterranean civilization with a very strict diet.
Okay, so let's break down their survival strategies, from the shallower zones to the really deep stuff.
Right. In the shallower zones, say between 70 and 2100 meters down, you find a lot of Erythrobacter. It's a chemorganotroph.
Meaning it gets energy from chemicals and eats organic carbon.
Exactly. Think of it as the cleanup crew. It's breaking down leftover organic molecules, fatty acids, polysaccharides that have sunk down over millions of years. It's a heterotroph. It eats leftovers.
So it's still connected, in a way, to the surface world. What happens when you go deeper and those crumbs run out?
That's where life has to shift to autotrophy, making its own food.
Right.
And here we find Thiobacillus. This one is a chemolithoautotroph. It's a rock eater.
So it's farming energy from minerals.
A perfect way to put it. It uses sulfur oxidation, and it fixes its own carbon using the CBB cycle, which is the same basic process plants use, but fueled by chemicals instead of light.
Okay, so Erythrobacter eats leftovers, Thiobacillus farms with sulfur. What's even deeper?
The truly deep dwellers, down to 2,800 meters, rely on an even older, more efficient strategy, the Wood-Jungdahl pathway.
And this group includes methanogens, methane producers.
Yes, the Methanobacteriaceae, they're archaea. The WL pathway is just incredibly ancient, and it lets them fix carbon with the absolute minimum energy possible. It's the ultimate slow-burn survival mode.
And the champion of this has to be the fourth key organism, Candidatus desulfuridus odoxiviator. The name sounds like an adventurer.
It means the bold traveler. It's a sulfate-reducing chemototroph, also using that hyper-efficient WL pathway. It was first found totally isolated in South African gold mines, almost 3 kilometers deep.
But its real importance is in its genetics, right? The evolutionary stasis.
This might be the most mind-blowing part of the whole DCO project. When they compared its genome from samples all over the world, they found incredible stability, an average nucleotide identity of up to 99.48%.
And in plain English, what does that mean?
It means its genome has barely changed at all since it diverged from its ancestors somewhere between 55 and 165 million years ago.
So, think about that timeline. 65 million years ago, the asteroid hits. The KT extinction event wipes out the dinosaurs and 75% of all life.
Right. The surface world was going through one of the most violent evolutionary bottlenecks in history. Total chaos.
And miles below, Audax Theater was just fine.
It experienced basically zero evolutionary pressure. It's remained genetically static ever since. It's a living, deep Earth relic. Almost immortal.
So we have a clear picture. The shallower zones favor heterotrophs eating old organic matter. But go deeper than 2 kilometers, and it's all about autotrophy.
Making your own food with these ultra-low energy pathways. Success isn't defined by rapid adaptation. It's defined by stasis and endurance.
But studying this kind of life, with such low biomass, must present a huge technical challenge: contamination.
Oh, it's incredibly difficult. The biomass is so sparse that a single human skin cell could completely throw off your results.
And the sources give a perfect example of this.
Cutibacterium acnes.
That's familiar.
It's an extremely common human skin microbe, and researchers kept finding it across 10 different deep groundwater sites from 85 to over 3,000 meters deep.
But it wasn't deep life, it was a contaminant.
Exactly. It was almost certainly introduced by the scientists themselves during drilling and sampling. It just highlights how delicate this work is.
And finally, all of this has massive implications for astrobiology, for the search for life beyond Earth.
It completely shifts the calculus of habitability. If life can thrive kilometers deep here without light or an atmosphere, then we need to change how we look at planets like Mars.
Or even the moons, like Europa and Enceladus.
Absolutely. The focus shifts from the surface to the deep subsurface to geothermal energy sources. One analysis even calculated the theoretical maximum subsurface biomass on Mars.
And what'd they come up with?
The estimate was, well, staggering. Roughly 70 million blue whale masses worth of potential life.
70 million blue whales.
Now, they admit that's a huge overestimate because it assumes 100% efficiency. But the point is, we should be looking at a planet's deep geology, its pressure and temperature, as the key to habitability, not just its surface.
It's just incredible. We've gone from Verne's fictional caverns and the hoax of a golden library all the way down to this quiet, ancient, massive reality of these microbial communities.
A community that outweighs humanity hundreds of times over, surviving by eating rocks.
So what does it all mean? What's the big takeaway for our definition of success, biologically speaking?
The biggest finding might not be the size of the biomass, but its incredible endurance. That stasis we see in organisms like Candidatus delphirutus audax viator.
A microbe whose genome has barely changed in tens of millions of years, while the surface world was torn apart by extinctions and catastrophes.
Which leaves a really important question for you, the listener, to think about. What does the existence of this successful, near-immortal, deep Earth civilization of microbes tell us about what's required for long-term survival in the universe?
When we look for life elsewhere, should we be looking for rapid adaptation and change?
Or should we be looking for this kind of incredible evolutionary stasis as the true sign of ultimate biological success?